The paper of the day is the Google file system. The Google file system demonstrates the qualities essential for supporting large-scale data processing workloads on commodity hardware. While some design decisions are specific to Google's unique setting, many may apply to data processing tasks of a similar magnitude and cost consciousness. Paper started by re-examining traditional file system assumptions in light of their current and anticipated application workloads and technological environment. Their observations have led to radically different points in the design space. They treat component failures as the norm rather than the exception, optimized for huge files that are mostly appended to, perhaps concurrently, and then read, usually sequentially, and both extend and relax the standard file system interface to improve the overall system. GFS provides fault tolerance by constantly monitoring, replicating crucial data, and fast and automatic recovery. Chunk replication allows them to tolerate chunk server failures. The frequency of these failures motivated a novel online repair system that regularly and transparently repairs the damage and compensates for lost replicas as soon as possible. Traditionally, they use checksumming to detect data corruption at the disk or IDE subsystem level, which becomes all too common given the number of disks in the system. Measurements. They measured the performance on a GFS cluster consisting of one master and two master replicas, 16 chunk servers, and 16 clients. This configuration was set for ease for testing. Typical clusters have hundreds of chunk servers and hundreds of clients. Now let's look at the contributions of the paper. Authors have re-examined traditional choices and explored radically different points in the design space. First, component failures are the norm rather than the exceptions. Second, files are huge by traditional standards. Multi-GB files are common. Third, most files are mutated by appending new data rather than overwriting existing data. Fourth, co-designing the applications and the file system API benefits the overall system by increasing their flexibility. They have relaxed GPS consistency model to vastly simplify the file system without imposing an onerous burden on the applications. They've also introduced an atomic append operation so that multiple clients can append concurrently to a file without extra synchronizations between them. Let's look at the conclusions. GFS design delivers high aggregate throughput to many concurrent readers and writers performing a variety of tasks. They achieve this by separating file system control, which passes through the master, from data transfer, which passes directly between chunk servers and clients. Master improvement in common operations is minimized by a large chunk size and by chunk leases, which delegates authority to parameter replicas in data mutations. This makes possible a simple centralized master that does not become a bottleneck. The belief that the improvements in the networking stack will lift the current limitations on write throughput seen by an individual client. GFS has successfully met their storage needs and is widely used within Google as the storage platform for research and development as well as the production data processing. It is an important tool that enables them to continue to innovate and attack problems on the scale of on the entire web. Let's look at the PS score. Overall, this paper is a delightful read, so it gets 10 out of 10 on readability. With 15 pages long, it scores 9 out of 10 on length. The description of the approach is exemplary, so that makes it 10 out of 10. It's an analysis and measurement of an internally developed system at Google. Its industry value and learning it is very high, so it gets 10 out of 10 on each. Overall PS score is 10 out of 10.